Good morning. Welcome to Biomedical Instrumentation. Today we will discuss the uh, sodium potassium pump theory. So to do so, let me share my screen first. So in biopotential generation, this is also called the sodium potassium pump theory. Why? Let us discuss. So in sodium potassium pump theory, this voltage we will call some resting membrane potential RMP, and the RMP is the starting point of bioelectricity. Now let us see that this particular structure, let us suppose to be this is one cell, and the cell is what? The cell is the smallest unit of the human body. Okay. So any cell, as you know, it is covered by some semi-permeable membrane, a membrane which is semi-permeable in nature. Okay. Now the inside that particular cell we have some intracellular fluid, and outside the cell we have some extracellular fluid. This is the inside of the cell. We have the intracellular fluid inside, and this is the outside of the cell. It is the extracellular fluid. Now, due to the semi-permeability in nature of this particular membrane, all the ions are not allowed to enter inside the cell. Similarly, all the ions are not allowed to exit out of the cell. Okay. So from the intracellular fluid, all the cells are not allowed to go outside of the cell, and from the extracellular fluid, all the ions are not allowed to enter inside the cell due to the semi-permeability nature of this particular membrane. And due to this virtue, there is some sodium ion concentration inside the cell is 30 times higher than the outside. Okay. And due to the same virtue, the sodium ion concentration is 10 times higher at the extracellular fluid than inside. Okay. Now, as you know, due to the Nernst potential, there will be some voltage difference, obviously, as there is some concentration gradient or concentration difference in between the inside and outside of this particular cell. So this particular, due to this concentration gradient and applying Nernst equation, we are having, or we there is a result of this concentration gradient. There is some 90 millivolt voltage difference in between the outside and inside, and this 90 millivolt we will call resting membrane potential. Okay. Why resting membrane potential? As this particular value, due to this much values of potassium ion concentration 30 times higher inside and sodium ion concentration 10 times higher outside, this particular value is not changing due to this uh, concentration gradients. Okay. And this is why this is it is called the resting membrane potential, and this particular millivolt has been generated as 90 millivolt. Okay. And arbitrarily we assume that outside it is positive, inside it is negative. This is only our assumption. The polarity may be different, but the total voltage or the total potential difference in between inside and outside, this is 90 millivolt, and this is fixed. This is called, this is we will call the RMP. Okay. So this RMP is the starting point of bioelectricity. Okay. So now this is what is cell. I have described over here. The cell, from Latin cella, means the small room, is the basic structural, functional, and biological unit of all known living organisms. So a cell is the smallest unit of life. Cells are often called building blocks of life. A living cell is surrounded by some semi-permeable membrane, which I have already discussed in the previous slide, and to passage to certain ions as chemical substances. Obviously, that is why some ionic concentration was maintaining inside to outside, and inside the cell there is some fluid called intracellular fluid. Outside it is called extracellular fluid, etc., etc. So whatever I have already mentioned, this has been pointed out over here. Okay, so the cell membrane, being the semi-permeable in nature, passes some ions to go outside of the cell, allows some ions to come inside in the cell, etc., etc. And ultimately, this the potential difference of 90 millivolt appears due to Nernst equation application, and which is assumed to be negative inside and positive outside. This is some assumption only. Okay. Now there is we have tried to electrically make the equivalent circuit of the cell membrane, which is semi-permeable in nature. So this is the circuit. We have tried to draw one circuit which is equivalent to the electrical equivalent of the cell membrane. And over here in this particular circuit, I have shown there is some capacitor. Okay, RK is the resistance which is 1 kilo ohm. EK is some battery arrangement or power source, DC power source. It is 91 millivolt. Similarly, there is some RNA whose value is 150 kilo ohm. RD is 38 kilo ohm, and ENA is some another DC power source whose value is 62 millivolt. And over here there is some voltage drop is generated. It is I have written as EC. Polarity I have given is it is positive, it is negative. Now let us see what is what in detail. So from this circuit, C, which was very left side, this capacitor is some capacitance equivalent to the cell membrane. Okay. EK, this EK is the Nernst potential due to potassium ion concentration gradient, which was 30 times higher inside. Okay, inside the cell. So that is why we have written 61.6 log 30 by 1 as 30 times higher than the outside. So it is approximately equal to 91 millivolt, right? Next one is the ENA. This one ENA is the Nernst potential due to sodium ion concentration gradient, which is 10 times higher at the outside than the inside. So that is why it is 61.6 log 1 by 10. It is the outside. See over here, due to the polarity constraint, we have mentioned this is the inside, outside, outside. Okay, so by application of logarithmic log base 10, okay, we got minus 61.6 log 10. That means minus almost approximately equal to 62 millivolt. Okay. Now RK is the relative permeability of the membrane due to the flow of potassium ion, which is equal to 1 kilo ohm. RNA is the relative permeability of a membrane due to flow of sodium ion, which is 150 kilo ohm. And RD, there was some RD. Okay, let us see what is this RD equal to. RD is the cell value of sodium ion concentration when the cell is depolarized. Okay, And EC finally at the right side, EC finally at the right side, this EC is what? EC is the RMP and assumed arbitrarily negative inside and positive outside. Okay. Now let us apply KCL, Kirchhoff's current law, on the given circuit. We get EK plus EC divided by RK, right? EK, let us see the circuit. EK plus EC divided by RK, right? Plus this will be what? This will be minus of ENA, as the polarity is, this is positive, this is negative for this power source. Okay, so which is the at the opposite direction of this applied achieved EC. Okay, we have assumed that this is positive, this is negative, and this particular ENA will be applied, has been applied as negative. So this is minus ENA plus EC divided by RNA. Okay, so EC minus ENA divided by RNA. Okay, that will be equal to 0. So it is EK plus EC by RK plus minus ENA plus EC divided by RNA, which is equal to 0. Now we replace the values. EK we have taken as 91 millivolt. As millivolt, it is 10 to the power minus 3 plus EC divided by RK's value. We have taken as 1 kilo ohm. Okay, 1 into 10 to the power 3 kilo ohm. Minus ENA 62 millivolt plus EC divided by 150 kilo ohms, that is equal to 0. Now after calculation, we got EC is equal to minus 90 into 10 to the power minus 3 volt, that means minus 90 millivolt. So our equivalent circuit, which we try to simulate the particular nature of the cell membrane through this particular circuit, is successful. And over here we see at the EC we get exactly 90 millivolt, which was the RMP, resting membrane potential, for the natural cells. Okay, so is there any queries? Okay, so now let us go to the next slide, which is to criticize the sodium potassium pump. How this particular pump is valid, now we will criticize. Now the first point I have mentioned is the metabolic energy expansion. That means while we take food, and due to the metabolism inside our body, okay, so this particular sodium potassium pump is being maintained. Okay, now supposed to be, if the cell is dead, what will be the voltage? The sodium potassium pump will not maintain its pumping. That means no ionic concentration gradient will be there, no inside 30 times sodium ion concentration gradient, outside potassium ion concentration gradients will be maintained. So that particular voltage drop will become 0. Okay, so if the cell is dead, the voltage will drop down to 0. Now the living cell maintains the concentration gradient, and due to that gradient we get the value of the sodium potassium pump, or the concentration gradient. After applying the Nernst potential, we will get the voltage is exactly 90 millivolt, which we take inside negative, outside positive arbitrarily. And the cell is unexcited. Unexcited means is that the cell has not given any stimulus. The cell is naturally maintaining its 90 millivolt. Okay, so the particular sodium potassium pump is maintaining at its natural rhythm and natural course. Okay, the cell is not excited. Now, supposed to be at some instant we have given some excitation to the cell. Okay, so how to excite the cell? We will put some stimulus to the cell. What is stimulus? Stimulus is a kind of excitation is given to the cell such that the cell will not maintain its natural sodium potassium pumping. Okay, so in unexcited uh, condition, the cell is not given any stimulus and it is maintaining some resting membrane potential, and the inside to outside voltage it is 90 millivolt. Now, what is stimulus? It is basically some excitement given to the cell, and the excitement means there may be we put some electrical pulses to be applied to the cell, some mechanical pulses may apply some pin, or some chemical stimulus which we can provide excitement we can provide in the form of injection to the cell, such that the natural 90 millivolt, the natural sodium potassium pump will not be maintained. Okay, so this is called some stimulus, and the stimulus may be of three types. Electrical one is the pulse. It is actually accepted due to the control is very good. That means up to how much time or how much severe excitation you can provide. Okay, the mechanical one and the chemical one is not so accepted due to the application control, which is not so accurate. Okay, and in chemical it is also not possible to control very controlled way. Okay, so we will give some electrical stimulus towards the cell. Okay, now after giving these particular electrical pulses, let us see how the RMP or that particular 90 millivolt is changing. Okay, so this is the wave nature after application of the stimulus to the cell. See, this is the RMP, which is minus 90 millivolt. Okay, this is the resting membrane potential. Now, if we provide some excitation to the cell, what will happen? There is some reversible conditions or reversible wave shape will be shown in the nature of cell. Okay, it will show some reversible nature. Is that initially it will be depolarized. That means the RMP, the value of minus 90 millivolt will be decreased towards the zero. Okay, then it will be reverse polarized. That means it is now getting some positive values. Okay, in the RMP, or we will not call it the RMP right now. Okay, it will have some another value than RMP. At RMP it was minus 90, but now while it is reverse polarization, that means it has got some value positive, that means greater than zero. Okay, it is reverse polarized. Then this reverse polarized state will retain for some time. Okay, as this is the x-axis time in second. After some time, this particular value, positive value, will be decreased towards zero, and after zero it will try to get to its RMP back in RMP stage. Okay, this is the repolarization. Okay, so from the positive value, the cell will try to get back its natural or RMP condition. This is the RMP condition, and this stage we will call repolarization, again polarized. Okay, so this particular action potential wave shape will have reversible waves or reversible conditions. First one is the depolarization. That means the from minus 90 millivolt, it is the value is decreased towards the 0, okay, then increase the value towards some positive value, and this peak value will be retained for some time, then it is getting back, trying to get back to its normal RMP. As the cell is live, it will try to get back to its natural RMP stage. So this particular condition we will call repolarization. Okay, so these particular actions, or all the actions, we in a single word we will call it action potential, as there is some actions has been taken and some reversible conditions, through some reversible condition it has gone through. Okay, so that is why it is called the action potential. Okay, now let us see what are the significances of the action potential. The significances of action potential is that this is the electrical signature of the cell. Electrical signature means what? That if the cell is some nerve cell, okay, if the cell is nerve cell, this particular wave shape will be different than the cell is some muscle cell. Okay, as we know, in the nerve cells, the speed or the velocity of the ions is faster than the muscle cells. So the travel of the ions will require less time to visit from one point to the another point. So this time will be less. Okay, as the ion travel time is less for the nerve cells, this time will be less as the speed is very high. So this action potential for the nerve cell we will see as some spike only, where this flat top will get some spike nature. But for the muscle cell, as the ion travel time is higher than the nerve cells, then we will see that this type of flat nature, that means the ion travel time will be much more, so the flat top will be achieved over there. Okay, so depending upon the nature of the cell, this particular wave shape will be changing. Okay, if it is a nerve cell, we will see some spike, and if it is one muscle cell, there will be some flat top, and the flat top will be happening due to some time. Okay, so this is the electrical signature of the cell. What the cell it is, it will obviously show while we apply the action potential. Okay, so the second point is the each cell has its own signature. What I have mentioned already is if it is the nerve cell, then it is a spike. If it is a muscle cell, there will be some flat top over there. Okay, so that is the own characteristics action potential wave shape. Okay, and the third one is that this has some clinical significance, obviously, that if the cell is infected with some external bacteria, okay, so obviously the resting membrane potential will not be same in that case. Okay, either it will be higher than 90 millivolt or less than the 90 millivolt, and the RMP will not start from minus 90 millivolt from here. Okay, either it will start from here, that means it will be supposed to be minus 70, or minus 110, it will be over here. So the same thing will not be achieved while the cell is infected with some external bacteria or viruses. Okay, so this particular action potential wave shape has a clinical significance, obviously. Okay, if the cell is diseased or infected with some external bacteria, the action potential will change, action potential is different for different cells. Okay. So is there any queries? Okay. Thank you.